So let's suppose, so your model, so the scores that we've talked about, when you plug an image into your DNN, goes through, spits out a bunch of log probabilities. Well, we need to convert those to probabilities using the softmax formula. So you give me a bunch of numbers, and they're going to look like negative 200, and negative 204, and negative 199, something. They're just some random numbers. And what we need to calculate is a vector of probabilities. And remember, the softmax formula is each of these entries is E. So let's call this the probabilities. So the ith entry in the probability matrix is E to the, and we'll call this the log probabilities. So E to the Li divided by the sum over Lj of E to the Lj. So we just have to take all these numbers, put them through an exponential, and then normalize, and we'll get probabilities. Okay, but what's the problem? What happens if you calculate E to the negative 200?
Numerical underflow.
You get underflow. It goes to 0. Similarly, if these were positive, and you calculated E to the 200, what would happen? They go to 0. Or sorry, go to infinity. Okay, so you can't just apply E to the thing when your numbers are bigger than, so like IEEE 64-bit floating point numbers, you can only represent stuff that's like 2 to the 300. And if you're trying to do that, you're doing something wrong. Like, things will break. Like, you just don't have that kind of precision. So what do? And the answer is the log sum x trick. So here's how it works. So let's multiply and divide this by 1. Okay? That doesn't change anything. Let's, instead of multiplying and dividing by 1, let's say we want to multiply and divide by e to the alpha over e to the alpha. So what happens if I multiply e to the alpha by times e to the alpha? Those add. And now, sorry, make sure we're clear here. What happens when I multiply this constant by this sum? I can just push this constant inside the sum. So that's sum over Lj, e to the alpha times e to the Lj. And what happens here? They add, so actually we can put this here. Okay, so what just happened? What this is saying is if you're doing log sum x, you can take your log probabilities and you can add any constant to all of them, and it won't change the results of your calculation. Okay, that's pretty awesome. So let's let alpha be the maximum over all j of Lj. In other words, go through this vector and find the max. And then instead of adding it, let's just subtract it. And what happens? Okay, yeah, so, I'm cooking with oil. Let's see. So, what happens if we subtract off 200? So, what the max is? Max is 204. What happens if we subtract off 204? You get 0 here, and you get negative 4, negative 5. Aha! What's e to the 0? 1. And what's e to the negative 4? I don't know, something small. Like something small, and this is like something even smaller. Okay, so notice, and then when you normalize this, you're going to get roughly like 0.99999, this is going to be 0.0001, and this is going to be negligible. Okay, so what happened? What this is saying take your log probabilities, subtract off the max, and now you will always have one number that is going to be 0. And e to the that will be 1. Everything else is going to be smaller than that. And so e to the that stuff will always be less than 1. So when you go to normalize this vector, you're like in happy land, because everything is neatly scaled for you. Another way to see this is if you imagine that we actually could compute e to the 204 divided by the sum of a bunch of things, one of which was e to the 204, everything that wasn't 204, that was less than that, essentially vanishes. And so you're left with e to the 204 divided by e to the 204 plus some small things. And the result is essentially 1. Okay. So the other thing to notice is that when you're thinking about probabilities, a difference of only 2 or 3 log points actually makes quite a big difference in like actual probability space. And if things are separated by more than like, I don't know, 10 or something, like probability get vanishingly small very, very quickly. Okay, so this is the log sum x trick. Take this, subtract off the max, and then do it, and you're good.
So is this supposed to be something we're implementing by hand in this lab, or is this something that there's a library they're supposed to be using and just understanding now?
I can't remember if PyTorch does this for you automatically. There's probably some function somewhere that'll do it for you. And in fact, under the hood, I forget, but if, like libraries that, for example, do sparse cross-entropy where you give it logits and an index, if it has to convert to probabilities, it will do this. Like it knows, everybody knows about this. But if you're coding it up by hand, then yes, you might consider this. This, by the way, is why it works fine when you plug it into Xavier. Sorry, when you plug it into PyTorch's existing library functions, it works fine. It's because they're doing this under the hood. But when you try to do it yourself the naive way, it explodes because you didn't do this.
Is there a reason why we do max? We don't do like the mean or the median of the list? Like, is there a reason why one?
Yeah, absolutely. So you definitely want to use the max because that will guarantee that at least one number will be in the right range. If you use the mean, so consider what happens. I mean, if my log probabilities were 1,000 and negative 1,000, and I tried to like subtract off the mean, well, the mean is 0. Like, it doesn't help.
Okay, so even though if you subtract 1,000, you have the other one be negative 2,000.
Right.
It's still.
And that's fine. Yeah.
I'm trying to make sure that I'm gonna remember like how those steps are the same as the name. So like in a sec, so we have those 3 arrows between those 4 little columns. And the second arrow, okay, we're exponentiating. Then the third one's doing what again? So going from the third
yeah,
part.
so we subtract the max.
Yeah, so subtracting, I'm like, okay, that's just, we
And then you
normalize it, so that'd be
exponentiate.
nice.
And then you normalize.
So where did we log?
You started off with logs.
Okay, so
I don't know.
they came
This
from logs
doesn't-
in the first place. Well, okay, well, like,
This is the name of the trick, the log sum x
this
trick.
was the math one.
It's because we're taking logs and we're trying to like
So
sum
those
and
came,
exponentiate
okay,
them.
those came from logs in the first place.
Yeah, while spitting out log probabilities for our
So we
classes.
spit out log probabilities and then we normalized them so that they would be nice to exponentiate.
I wouldn't use the word normalize here. I would say that you shifted them into an
Okay,
appropriate
shifted.
range.
So then where did the word sum come from?
Well, you have to sum
Oh,
it up when
okay,
you
we
actually.
normalized to sum.
There is a
Okay.
normalization step that involves summing it so that.
All right, so now I see there's a log of sum, but they're just not in that order.
Yeah, so it's like the log sub x sum divide trick.
Log shift x sum.
Yeah, okay,
Okay.
good. Any other questions? Just quickly, we gotta get moving
Does
here.
it matter whether you set a batch or instance level? Like whether you...
You should do this on an individual prediction level. So for each element in the batch, it should be done independently. Yes. Yeah.
Why do we not just like subtract out the minimum and divide by the maximum? Why do we use soft max instead? Because that would like shift it between 0 and 1. Is there some principal reason why the soft max is better than just squishing them all?
I think that working in log space is generally preferred, like whenever you can. I just imagine that the gradients will flow more nicely through this than it would through if you try to spit out unnormalized probabilities directly. Okay, let's move on to the rest of the lecture then. Hopefully this is helpful to you as you think about. And thank you. There we go. I'm lucky I have you guys. Okay, so today I want to talk a little bit more about getting things to work. high on the gradient to regularization. So getting things to work. So I showed this slide very briefly, and these are just some rules of thumb. So as you begin to design your own neural net topologies, I think you'll find sometimes things work and sometimes things don't, and you don't always know why. These are just some best practices that we've harvested over the years, and I think that I think that we've already actually talked about a lot of these things. So for example, use ReLUs, don't have that activation as your output layer, add bias, variance scaled initialization, this is another word for Xavier, so use Xavier initialization. Whiten or normalize your input data. So we didn't really talk about that. Can anybody imagine why that might be useful? And first of all, what does this mean? Okay.
So when we have our image, it can range from 0 to 255.
Right.
Type is in into and cause different issues, so we normalize those pixel values, which is 1, 0, and 1, so it makes sense.
Yeah, okay, so Adesha's got the right idea. So the idea is, if you were to take an image and the numbers in your images were numbers between 0 and 255, and you just plug that into a neural net, what would those 255s do as they cascade through your net? It's kind of like, yeah, it's kind of like big weights. These are big numbers, and they're going to start causing things to explode. So a much better idea is to take your data and just scale it so that your data is mean-centered and white. So you just subtract the mean, divide by the standard deviation. So this is a simple pre-processing that you should always do. And then you have numbers that are about the right scale flowing through your network. Yes?
Is that something we have to do explicitly or just?
Yes. You need to do it yourself. The reason is PyTorch has no idea. It doesn't, like, just the way it's set up, it doesn't know that it should do that. There's no way it could know that.
So you said mean center? You
Yes.
mean 0 center, or what do you mean by mean center?
I mean, subtract off the mean, so it's 0 center.
Okay, gotcha.
Okay? And a couple of other rules, we'll talk about these later. But what I wanted to talk about today was debugging your network. So designing your network is one thing, but debugging it is an entirely different thing. So let's talk about some of these rules, and we'll go through as many as we can today. So first of all, overfit. Now, why would I throw that up as the first thing that I want you to do when debugging a neural net? Yeah.
Because it means it's learning.
Right. Okay. So here's like my thinking on this. You give me a neural net, you say, Dr. Ringe, this isn't working. I say, okay, let's try to overfit on just one example. So we're going to get rid of your batches, we're going to get rid of your data loader, we're just going to have one image. And we're going to try to get your neural net to train on one image. And if we can't do that, then something is really wrong. Probably your network isn't hooked up right. Gradients are dying, something's vanishing. Maybe your computation graph is like more like a computation like stack of wood or like pile of splinters or something, like it's fragmented somehow. So we say, let's try to overfit on just one example. If we can do that, then we can begin to see what happens when we try 2 examples or 3 examples or whatever it might be. We can tune other things. Okay, lower your learning rate. We've talked a little bit about learning rates. Why would lowering the learning rate help us debug a neural net? Yeah.
If your learning rate's too big, you might be making big steps and you're just lost because you never actually learned where you want.
Yeah, right. I mean, maybe that we need to be a little careful about tuning our weights. If our learning rate is too big, and we might just be hopping around. There's maybe some beautiful global minimum, but we're stepping over it. And so we need to take small steps so that we go downhill and find the bottom. Okay? But raise your learning rate is the next rule. Why? Why would that help us debug a neural net? Yeah.
Get out of the local minimum?
Get out of the local minima. Yeah, maybe our learning rate is too small and we're just like at the bottom of a valley and we can't ever get out. Okay?
Doesn't Adam, the optimizer, change your learning rate for you?
Yes, and we'll talk about this. But there are parameters, there are hyperparameters to Adam, which still matter.
Yeah, that was my question. I've never understood why we pass the learning rate into it if it changes.
It's not the same as a true learning rate. It's something related to a learning rate, but it's a hyperparameter. I mean, when we talk about Adam, we'll talk about what that number is. And there's actually more than one.
Yeah, I was just wondering, since we're using it for this lab, if we should worry about our
No,
learning
you
rate.
shouldn't worry about it.
Okay.
Yeah. Okay, how about increase and decrease your batch size? How would that help us debug? What do you think? ask you this. Why would increasing your batch size be a good idea?
Maybe you could find a more true gradient.
Yeah, so the more items we have in our batch, the less variance we're going to get in our gradient estimates. We're going to get cleaner gradients. So what we're saying here is we're saying maybe there's too much noise in your gradient. Now, why would I say decrease your batch size? Yeah,
Because it's not taking gradient steps often enough.
right. Maybe we can try more. Maybe we just need to take more steps. So smaller batches will go faster. We'll be able to take more steps. Okay. Remove batch norm. Sometimes it causes problems. Check your reshaping. We'll talk about this at length. But there's times when you're going to take tensors and you're going to reshape them in funny ways. And you just need to make sure that the reshaping that you're doing is like what you think it's supposed to be. And then finally, scrutinize your loss function. So let's talk about the loss function just a little bit. So I think it's very important when you're calculating things and you're calculating things like the loss of your neural net that you don't just see a number. Hopefully it's a number that makes sense. So for example, here's a little model. Let's see if we can kind of imagine, it's like this kind of pseudocode Python code. Let's see if we can imagine what's going on. So we have some input, some hidden, some output. Got some numbers here, some stuff, some numbers. Okay, return a model. We have a little 2-layer model, and we are going to, calculate some loss. Let's suppose that this is a 10-class classification problem, and when you spit something out, and you're using like cross entropy, you get a number like 2.3. Why is that correct for 10 classes? Why is that about the right number? Like, if this had said 16, I would have said not the right number. 2.3, that's the right number. Why? I want you guys to talk about it. So let's talk about this. Get in your groups, talk to your neighbors, see if you can figure this out. Why is 2.3 the right number? Okay? Take a minute. We only have 10 minutes in class. Let's go ahead. See if you can figure this out.
Worst case scenario is you're absolutely certain